So this is the final session of talks for this year's Open Programming Miniconf at linux.conf.au. We've got a couple of talks on concurrency related stuff, followed by our lightning talks, and it looks to me, just looking at the board up the back, that we actually have a full contingent of lightning talks. So we should be going through to the end of the day, which is really good. And if you could please make sure that your mobile phones and tablet devices are set to silent. I'll give you a moment to do that. Everyone's done that? Good. Okay, so our first presentation today is being presented by Tim McNamara, who leads outreach activities at the New Zealand eScience infrastructure. He's also been a past convener of Kiwi PyCon, but today he's going to be talking about what we can learn from Erlang. Please make Tim welcome.
Hey, thanks very much, Chris. And also, it's been great to fly over to Australia. It's a lovely, lovely warm place with tons and tons of crazy bugs. But Erlang. The objective of this talk is really to give application developers, library authors, and possibly even programming language developers a little bit of a sense of some of the tools that Erlang uses to really provide a lot of performance and especially reliability to systems that are built with its platform. With the very, very large caveat that I'm not the world's greatest Erlang programmer. I've only sort of started with the environment, I guess, really 6 months in earnest. And that wasn't even that earnestly, but I've just been really intrigued by a radically new way of developing software. So to get straight to the conclusions, if you can send messages between isolated, potentially unreliable processes or components, you can spread your application anywhere. If you have a reliable, you can let things crash and just trust that your supervision hierarchy will just reboot things to a clean state. It means that you can actually be much more free with how you write each of those individual components. And internally, you'll also need to kind of create some registry service so that you won't be hard coding port numbers or host names. Hopefully you can just ask to talk to, in our case, the computer vision function or the computer vision service in our application, and then the application can actually decide where it lives and where the computation will be carried out. So I saw this on Reddit. So Erlang is in many ways not the most popular of programming languages, but there are some good things, and I thought that we'd explain with like a telephony application. The way that Erlang does its work is by splitting applications into many processes. In this case, we've got worker kittens on the phones. This talk is going to focus a lot on how they communicate, those worker cats, and we'll actually try and emulate this with a couple of open source tools effectively in language agnostic manner. We've already sort of talked about the fact that we can separate our application into small independent components. Another advantage of that is that we could kill one little bit without having the error ripple through the rest of our system. So yeah, why Erlang? These benchmarks that I'm going to provide here aren't so much to even be hysteric about it. I just wanted to provide a little bit of strength behind the claim that Erlang systems are reliable. And you can actually get some decent performance from relatively commodity hardware, in this case, commodity virtualized hardware. Well, that one really did not render properly. I apologize for that. Okay, so, what can I explain here? Okay, the very top line is actually the headings, and the second line is Erlang. It's a message count. Over the right is 0. You can see that there's one character. And then there's a whole bunch of other systems, including I think there's there's Node, Node.js you can just kind of make out. So apparently when the thing was rendered on, anyway, no messages got lost. It was 10,000 concurrent connections and no messages got lost. Here's some similar kind of thing. We have here 50,000 messages, HTTP messages to a couple of web servers. The top two, Cowboy and Mitsultan, are sort of Erlang projects. The Cowboy one has now kind of taken steam there, but they make it very, very hard to lose messages. Oh, and just for fun, this is attacking a Raspberry Pi with Siege. You can give it 100 concurrent connections for 30 seconds and maintain 100% availability. So just a couple of words about what an Erlang process means, what that word actually means. It effectively, the way it looks like, it's just a function call, except that you also have your own heap, your own stack, and your own message box. So each process can receive messages and act upon them. And this means that if I kill one Erlang process, or if the Erlang virtual machine decides to kill it, those errors aren't going to propagate through the rest of the system because the memory is in many ways partitioned amongst the rest of the system. So if I die as an Erlang process by a supervisor or hierarchy of supervisors, and if I die, Erlang will send my supervisor a message and then allow the supervisor to either restart me, or if it's like a clean exit, just allow the program to kind of close down. So this is some of the other things that you get as an Erlang programmer. So we've talked about isolation, the fault detection and supervisions, supervisors restarting things for us, guaranteed message delivery, distribution. By that I mean that you can actually move any of these services between, say, cores on a chip, or between chips, or between hosts, or even between data centers in the case of a system like React. And in fact, you don't need to change any code in your system at all. That's what the runtime provides for you. It uses a registry, so you can register a process, and that will be registered either locally within one node or globally amongst every node that your system is connected between. It's got a very efficient scheduler as well between possibly hundreds of thousands of these little processes. You can upgrade code on the fly, and you also have remote shell access into your whole cluster. We're going to be killing the bottom two for this talk, but I thought we could have a go at doing something similar about the rest. So Erlang is providing everything. I'm bringing in a little bit of jargon here, OTP, because if you do any Google searches, you're inevitably going to encounter the term OTP. It's effectively a set of conventions that the Erlang/OTP community uses to build a hierarchy of process and workers. It's nothing more than but they're fairly well baked into the language now. They are kind of the standard. If you're an Erlang programmer, you'll be using what they call the OTP design principles. It was an initialism for the open telecom platform, but it's really moved away from that specific use case and is now just a general way for building services in a hierarchical manner. So here's a go at what it might look like if you were to build things yourself. So if you need a scheduler, you may as well just use the operating system. It can schedule between processes. If you want process isolation, you can use operating system processes. I think 0MQ is a pretty nice way to deliver messages around between systems, because just as before we could move between a chip, a cluster, and then maybe even between data centers, you can move in 0MQ between inter-process communication to TCP or even over UDP multicast if you want as well. And protocol buffers, the reason I've included them there, they're not strictly necessary, but I like the idea of providing valid and typed data between my applications. Protocol buffers have they are a very, very trivial cost in terms of deserialization, and they provide you some guarantees about the fact that if you receive data in the correct manner, that it will be what you send. Or at least, if you send an integer, you'll get out an integer, is what I mean by that. So supervisor kind of does, it's fairly easy to use. It's just a config file, and it will reboot things if they fall over for you. And I thought the way to implement a naming system would be Redis. One caveat there though is that Redis isn't going to provide like a it doesn't have clustering support yet. I've heard that it's in the works. Oh, that was me. So we'll just go past all the reason why. I thought that I had to put some code, so here's a Python implementation of a service, or so this is the abstract class. And I haven't tested it, so this is kind of analogous to what something would look like, but let's have a go. So the first thing I want to do is initialize myself with some registry. So I'll register myself on a name, and we just hope that that register method, which I haven't included here, goes and calls that Redis database and says, I'm now alive. Please route any messages back to me that have my name. There's also a main function. All the main function does is call a while loop. But if there are any exceptions, I need to close down fairly neatly, but I also want to inform the rest of the world that I have died. So that's what that exception is. One thing that I forgot to mention is that message underscore types. This is some notional module that includes the protocol buffers implementation. So we're using two protocol buffers here. One is an arguments array that we can use to send, we'll be using later in the loop, and the crash report. So I provide the name that I am, the fact that I've crashed, I'll send the exception in, and maybe the last known good state. So that if my supervisor wants to restart me, it can start with something that I knew it won't just repeatedly crash itself and really die. And I'm just sending it to this notional control service, which itself would be implemented as one of these services, so that what that lets you know is that this thing here isn't the right implementation. It's just some, because the control, if you were to implement this with a service named control, it wouldn't be able to call itself if it was already dead. The loop, translate the current state into our last known good state. It will then initialize an arguments array, which is a protocol buffer, receive a multi-part message from 0MQ. 0MQ, you can send multi-part messages, and it will provide a string that will be a function to call, and the arguments along with it, wrapped up as one of these messages objects. We're just doing some args.pass from string as a method with protocol buffers. This arguments to list is something that isn't implemented, but I thought it would be fun to put in there. And then we dispatch. So if anyone hasn't used Python and this thing here is looking extremely odd, getAttr takes an object and a string in this case, and it actually goes and gets the attribute that object refers to. So what we're getting at here is a method that will be this string, and then we just apply those arguments to it. The star will expand a list into a function call. And this is actually implementing that service. So if you wanted to create an API, you would just create a method called detectFace, or detect underscore face. And because of how we've used getAtta, Python will know what to do here, because it will find an attribute with the name detect face for our computer vision service. And this if underscore underscore name is equal to underscore underscore main is just a sort of a Python idiom that says if I'm being run from the command line, which supervisor will kind of emulate, because supervisor daemon is starting this up, then initialize the object with the name CV and start that main function, which itself then calls the main loop. You'd also want, if you were to do this for real life, you'd want to implement some decision about what I do if I get a message that I don't know what to do with, because that would be important to do. There might be some genuine reason why I would need to shut myself down. Maybe the system is going down completely, and code change. I said that I wasn't going to talk about it, but let's talk about it. So yeah, Erlang has this, this kind of mythical unicorn property whereby it will promise you that you can change your code on the fly. What it does is in this loop that a lot of its servers are used to operating in, it maintains a state object. Well, it's a tuple, and when it receives a message to change its code, it just refuses to go into a new version of the loop. It will pass its current state back to the sender, and then the supervisor creates something with a new name. So what ends up happening is that things that are currently running are not affected, but any new services that, say, talk to this new computer vision version of the code, because it will actually run on the new code. So I just thought I'd reiterate that with what we've kind of covered across. Sending messages is good. It means that everything is isolated and we don't propagate errors. And it means we can achieve things like real-world performance. Apparently from one Ericsson product has achieved 9 nines of reliability in real life, just from this ability to update code, and for one failure in some small edge case not to ripple out and explode into the rest of the system. It's in many ways the complete opposite model to the embedding system, or the embedding architecture that we just kind of heard a couple of talks about. You try and keep all of your components as far away from each other as they can, and they can only talk using messages. It's the only way to share data. And we haven't gone into the implementation of a registry system because I didn't think that it would be particularly useful, and I knew that I would do it even badly than that service class that I created just before. How much time do I have?
7 minutes, including questions.
Okay, well, I just thought I'd tack in some interesting other things about Erlang. It's pretty much impossible to do blocking I/O in Erlang. I think that if you're a library designer or you were thinking about a way to do a program, just don't allow your to do things that are going to block the whole process. There is a compact binary type, so that if you have something that's longer than 60 bytes, Erlang will only pass a reference to some arbitrarily long binary, and we'll accept that as part of a list structure called an I/O list, which can vary. If you just send it to a socket or a file, this I/O list type or object, Erlang will flatten it out, and if you send it a byte or in the list, an integer in the list, it will just send the equivalent byte. If you send it a binary, it's just going to send all the binary data to the file or to the socket. And if you send it a string, it's going to send the string out. And if there's another list in there, it's just going to unwind the nesting for you, which I think is extremely convenient. Erlang also in the standard library has a database called Amnesia. It's super cool. You can add new nodes and it will distribute equally either on disk or in memory, and provide things like atomic distributed counters, which so if you're ever interested in how are distributed programmers distributed algorithms implemented, you could look at that database, but it also provides a very good default for application developers about when they think about where am I going to store my data. ETS is the Erlang term storage. It's just an in-memory database. And then DETS is the disk Erlang term storage, which both together are actually used to create amnesia. That kind of comes to the end of the things that I was going to say. If you're interested in talking to interesting people, Erlang is probably a great place to hang out. It's much more casual than, for example, #Python or #Python in Freenode. And it's an interesting community, and hopefully this talk has been fruitful for you.
So, are there any questions for Tim? Great, so you first, then you.
I'm just wondering what the runtime requirements are for Erlang, and whether it's possible to embed it in hardware of the order of Raspberry Pi. I noticed you.
Yeah, Raspberry Pi definitely. Erlang was originally developed in the late 80s, and it was for embedded devices. It started in the embedded world because Ericsson makes telephone switches and things that just can't break out in the middle of the desert. There's another question up the top. But I don't know how small you can go. It does run on a single-threaded machine or a CPU, but it will kind of create its own operating system with all these processes.
You've given some great examples of what Erlang does and how to emulate in other languages. Is there a reason not to just use Erlang in the first place?
Yeah, I don't. Actually, I've been thinking that myself, right? You've got this great runtime, and so what I've ended up doing when the project I've started in is sort of building the web front end or the web back end in Erlang, and then have just Python workers, which can actually act in a very, very similar way. So if you have things that just need to serve a lot of users, Erlang can be a great tool. I mean, the syntax is scary, and there are a lot of conventions. The business is quite difficult to get your head around. Erlang has some other hard things for people. Like, I come from a Python background, and Erlang wants you to split individual modules into individual files. And so one application might have 6 files because of this OTP system has a number of conventions which mean that you create a supervisor or a couple of supervisors plus a worker thing, and they each need to be in their own space. And I found that just mentally to be a little bit difficult. But, yes, sorry.
So Erlang's a strictly functional language. If you were implementing it in Python or some other language that allows mutation of variables and state,
yeah.
Would that cause problems for the synchronization across?
Yeah, so I've relied, the question was, as I understood it, Erlang's purely functional, there's only single assignment, for example. What if you mutated variables like Python does? In fact, in that code example, I mutated a variable. I rely on the fact that the OS process is going to make it extremely difficult for me to require shared memory between processes. But yeah, again, if you want to just use the benefits of Erlang, one approach is to just use Erlang. So I just thought it would be an interesting kind of mental experiment just to demonstrate why they've done why they've made some of those decisions that the OTP team has.
Is that it for? Eric?
One of the things about the Erlang processes is that they are very, very lightweight processes, and running hundreds of thousands of these very, very light processes is pretty trivial even on a pretty restricted machine. The same is not the true for OS processes.
Yeah. So in the Erlang world, process creation is measured in microseconds, not milliseconds, and you're talking about maybe 400 words of memory, so less than a kilobyte. I wouldn't operate in, so for example, almost every web framework will spawn a new process for every request. even at the volumes that we were sort of demonstrating before, I wouldn't go that far. So you can't do Erlang outside of Erlang because it is opinionated, and they've created an extremely optimized runtime for doing what they want to do.
I think we'll call that time. So everyone, please thank Tim.